Have you ever wondered how a really clever piece of code can solve these massive, complex problems? From predicting financial markets all the way to solving weird survival puzzles? Well, today that's exactly what we're going to do. We're going to put on our programmer hats and really explore the power of what we call algorithmic thinking. We'll see how some structured, elegant logic can unravel some truly fascinating challenges. So let's just dive right in.
Okay, so let's start with a practical puzzle. Imagine you've got a full year of stock market data. You know what that looks like. It's a total roller coaster of daily gains and losses. Now, your job is to find that one single unbroken stretch of days that would have made you the most money. And remember, it's not about picking the best individual days scattered around. It's about finding the single most profitable period. So, where would you even begin with that?
Well, this isn't a new question, not by a long shot. In the world of computer science, this is actually a classic challenge, and it has a name: the maximum subarray problem.
Now, the T word here, the one that changes everything, is contiguous. That means we can't just cherry-pick the good days. We have to find an unbroken sequence. It could be a week, maybe a month, or any stretch of time where the total profit from that one period is higher than any other possible period in the whole year.
Now, you could try to solve this with what we call a brute force approach, right? You could literally check every single possible start date and end date. But with a year's worth of data, you're talking about millions of combinations. It's just incredibly slow and inefficient. Luckily, there's a much more elegant, a much smarter solution called Kadane's algorithm.
The absolute beauty of Kadane's algorithm is just how simple it is. We only have to go through the data one time. We just keep track of two things: the best profit we've found so far, and the profit of the current stretch we're looking at. As we move to the next day, we just add its value to our current profit. And here's the magic trick. If our current profit ever drops below zero, it's a lost cause. It can't possibly help any future period, so we just drop it, reset to zero, and start a brand new stretch from the very next day.
And check this out. This is the entire algorithm in just a handful of lines of Python. It's so clean. We loop through our numbers, adding each one to our current sum. If that current sum ever dips below zero, bam, we reset it. And at every single step we check, hey, is our current sum the new best sum? That's literally it.
So let's just walk through this example run. We start with -1. Our current sum is -1, which is less than 0, so we reset it to 0. Next up is 2. Current sum becomes 2, so our best sum is now 2. Then we add 3. Current sum is 5, so our best sum is now 5. Next, we add 4. Current sum jumps to 9, so best sum becomes 9. And finally, we add -3. Our current sum drops to 6, but that's less than our best sum of 9, so we don't change anything. And there you have it. The algorithm correctly finds that the subarray 2, 3, 4 gives us that max profit of 9. Perfect.
And this algorithm isn't just for stocks and finance. Not at all. The very same logic is used in computer vision to find the brightest continuous area in an image. It's also used in genomics to identify really important segments in a DNA sequence. It's this fundamental pattern for finding the best stretch of pretty much anything you can imagine.
So an algorithm is only as good as the data it has to work with. And how we organize that data, well, that's just as important as the algorithm itself. This brings us to the really crucial concept of data structures.
When you think of a list of numbers, you probably picture them all stored neatly side by side in memory, kind of like houses on a street. That's called an array. A linked list is totally different. It's more like a treasure hunt. Each item holds a piece of data, and then it holds a clue, a pointer, that tells you the location of the next item in the chain. The items themselves can be scattered all over the place in memory.
So why would you ever use one over the other? Well, it all comes down to trade-offs. Arrays are amazing for quick access. If you know an item's position, say item number 5, you can jump right to it instantly. But adding or removing something from the middle? Oh, that's a real pain, because you have to shift everything that comes after it. Linked lists, on the other hand, can grow and shrink really easily. To insert or delete an item, you just have to change a couple of pointers. It's incredibly efficient for those kinds of operations.
The basic building block of a linked list is something called a node. It's super simple. It's just a little container with two parts: the actual data you want to store, and then the pointer, which is really just the memory address of the next node in the chain.
And here you can see it in action. The first node's pointer is just holding the address of the second node, and that's what creates this directional link. It's the first step in building our chain.
And this is what a complete list looks like. We always keep track of the very first node, which we call the head.
From there, we can traverse the list, which is just a fancy way of saying we can move through the entire chain by following the pointers from one node to the next, all the way until we hit a null pointer, which just signals, hey, you've reached the end of the list.
All right, so now that we understand linked lists, let's use them to tackle a famous and, yeah, a slightly grim computer science puzzle, the Josephus problem.
The problem goes something like this. You've got a group of people standing in a circle. You start counting at person 1, and let's say every third person is eliminated. The counting just continues around the now shrinking circle until only one person is left. The big question is, can you predict where you should stand to be that sole survivor?
The thing that makes this problem tricky is that the circle is dynamic. Every time someone is removed, the circle shrinks. Trying to do this with a standard array would be a total nightmare, because you constantly be shifting elements around to fill the gaps. This sounds like a job for a very special kind of linked list.
And this is the perfect job for a circular linked list. It's exactly like a regular linked list, but with one key difference. The very last node points right back to the first one, creating a seamless loop. To solve the problem, we just move k-1 spots, we remove the kth person, which is super easy, we just change the pointers, and then we start our next count from the person who came right after.
And here's the Python code to do it. It's so elegant. We have a loop that runs as long as there's more than one person left. Inside that loop, we find the person to remove, we update our starting point for the next round of counting, and then we remove them from the list. The loop just keeps going until only one person remains, and that's our survivor.
So from maximizing profits in the stock market to, well, surviving a deadly circle, we've seen that choosing the right algorithm and the right data structure is so much more than just some academic exercise. It's a genuinely powerful way to solve incredibly complex problems and to do it efficiently.
And that's really the key takeaway here. The programming language, whether it's Python or Java or something that hasn't even been invented yet, that's just the tool. The real skill is learning to think algorithmically, to break down a problem and build a logical, efficient path to a solution. That is a skill that will last you a lifetime.
So, I'll leave you with a question to chew on. What problem, in your world, in your work, or just in your life, is just one elegant algorithm away from being solved? Thanks for exploring all this with me today.